problem, you're always working with moles per liter. Or grams per liter. Then you have to make corrections as you go along. All right. At any rate, number 10. We want to know if we mix equal volumes of those two ions in solution, will a precipitate form? Well, let's see. Concentration of the silver is going to be 1.5 times 10 to the minus fifth. The concentration of the bromide equals 4.8 times 10 to the minus 6. I want to know, am I going to get AgBr? Okay? Will I get a precipitate of AgBr? So what I'm going to do is I'm going to look up the KSP of AgBr. I'm going to go to my solubility product chart. There it is. Silver bromide is 5.0 times 10 to the negative 13. Okay? Now we worked that equation, we worked this here from this. You get that, right? So, KSP will be concentration of silver times the concentration of the Br. Well, let's see. I don't want KSP. I'm going to make a minor change in this. Because I don't know if I'm at equilibrium or not. So if I don't know if I'm at equilibrium or not, this K becomes a Q. Okay? So now I'll figure out QSP. The QSP is going to equal (1.5) times 10 to the minus fifth times 4.8 times 10 to the minus 6. Multiply those two and let's see what I come up with here. We'll take 1.5 exponent minus fifth times 4.8 exponent minus 6. Comes out to be 7.2 times 10 to the negative 11. Okay. How does that compare to the KSP?
It's larger.
It's larger, right? The QSP is larger than the KSP. Since it's larger, you get a precipitate. So the answer would be yes, you get a precipitate. Okay? This is a good example of show your work. Okay, if I see the work, I'll base partial credit on what you get. But if you just put down yes or no, you're taking a 50-50 chance of getting it right. Okay? You either get full credit or you get nothing. So make sure you get some work in there to show how you go about doing it. Okay? And in this case, what we find out is since the QSP is larger than the KSP, we get a precipitate. If it was smaller, we would not get a precipitate. Okay? Okay. All right. Let's take a look now at the last few problems which deal with electrochemistry.
Our test is going to be very similar to this.
Good?
Our test is going to be
Very similar to this, yeah. People get upset because they use different numbers. Okay. As a matter of fact, I talked to Professor Himes, he says it's just, not too kind of me to use different numbers on the problems. What I should do is I should use the same numbers and just change the answers. Anyway. Okay. Now, all right, let's see. Laboratory experiment, a student deposits nickel from nickel 2 plus. All right, so if I'm going from here, if I'm going from nickel 2 plus to nickel, that's a change of how many electrons? 2 electrons. So I'm going to need that somewhere along the line, so let me put that in here. I'm going to need 2 electron change. Okay? Let's see what else it tells us. It tells us that we're going to go for 35 minutes. Okay, 35 minutes. At a current of 0.65 amps. Okay? And we want to find out the grams of nickel. Okay. Let's find out how much electricity we use, the number of coulombs. Coulombs equals amperes multiplied by seconds. And I got minutes there. I got to change it to seconds. So I'm going to take the 35 minutes, multiply it by 60 seconds in a minute, and I get 2100 seconds. So the 35 minutes equals 2100 seconds. So my number of coulombs will equal 0.65 amps multiplied by 2100 seconds. Which comes out to 1365 coulombs. Okay? Once I get that, my next step is, how many moles of electrons are involved? So, the moles of electrons equals the coulombs divided by 96,500. Okay? So if I take 1365 divided by 96,500, I come up with 0.0141. Moles of electrons. Okay, that'll give me my number of moles of electrons. Now, since each nickel involves 2 electrons, she told you I was going to need that 2 somewhere along the line. since each nickel involves 2 electrons,